Hello everyone. In this video, we'll talk about 4 practice problems on linear regression. These problems have been taken from interviews for data scientist role. Now, if you're interested and to know more about linear regression, we had done some videos previously and shared them on YouTube. You can find all of those links in the description below. This last link is of Khan Academy, where it explores linear regression by solving some basic numerical problems. Now let's look at the problems which we had. The first question was asked to me direction. The question goes, you're given the data generated for the following equation, y equals to x to the power 9 multiplied by 3. Can you apply linear regression to learn from this data? I'll give you a minute to think about it and then we'll look at the solution together. All right. So equation of line is y equals to mx plus c. Equation we are given is of the form y equals to x to the power m multiplied by c. So the steps which we follow are, you have to know a little bit of logarithms to solve this problem. You take the log on both sides, apply the multiplication rule, then apply the power rule, and what you get is a equation for a line itself. But the terms are logarithms. Basically, this equation log of y equals to m into log of x plus log of c. Here it can be treated as a equation for line y equals to mx plus c. So the answer is yes. This data, if you can solve, you can apply linear regression to learn from this data. The next problem was asked to me at Infosys for digital solution specialist role. If you do linear regression in 3D, what do you get? I'll give you a minute to work on it yourself and then we'll look at the solution together. All right, let's look at the solution. When you perform linear regression on 3D, essentially you are fitting a plane to a set of data points in 3-dimensional space. The general form of equation for a plane in 3 dimension is z equals to ax plus by plus c. So this has given you some hint. So basically, when you fit a line, when you do linear regression to a 3D data, what you get is a plane where you try to predict z based on x and y. And here, like z equals to ax plus by, z is your dependent variable, x and y are your independent variable, a and b are your coefficients that determine the orientation of the plane, and c is the intercept. Now, in general, this concept can be extended to n dimensions, and if you do linear regression in n dimensions, what you get is a hypersurface in n-1 dimensions. Now the next question is asked to me at Infosys for digital solution specialist post. How do you tell if there is linearity between two variables? So there are a couple of ways to do that. First way is to draw a scatter plot of the two variables. If you see that the two data points roughly form a straight line, either increasing or decreasing, there is likely a linear relationship. Next is correlation coefficient. If you find the correlation coefficient and that correlation coefficient is close to 1 or -1, that means there is linear relationship between those two variables. If it is close to 0, then it shows weak or no linear relationship. Now you can actually fit a linear model to understand the relationship between those two variables, and it will give you a equation of line for representing y with respect to x. Y is one of those variables and x is the other left out variable. Now, once you have got that equation of line, it basically you have fitted a linear model to the data, and then the next step is to do the residual analysis. Examine residuals. Residuals are differences between observed and predicted values from the fitted linear model. Now, in residual plot, if the residuals are randomly scattered around 0, then there is linear relationship. If the residual show a symmetric pattern, example a curve or a trend, there is non-linear relationship between the data points, between the two variables. Now, I'll skip the statistical tests, but it is not very complicated, but you have to know hypothesis testing to understand it a little bit better. But the sixth one is fairly easy, which is coefficient of determination. So calculating R square value, which indicates the proportion of variance in the dependent variable explained by the independent variable. A value close to 1 indicates a strong linear relationship, and value closer to 0 indicates a weak or no linear relationship. Now the next question that is coming up was asked to me at TCS and Infosys. What is the difference between lasso regression and ridge regression? I'll give you a minute to think about it, and then we'll look at the solution together. All right, let's look at the solution together. So ridge regression is the penalty type. Basically, ridge regression, the difference between ridge regression and lasso regression is in the penalty type. This term. This is the penalty term. In lasso, this is the penalty term. Now you can see in ridge regression, the penalty term is squared magnitude of coefficients. Sum of squared magnitude of coefficients. And in lasso, sum of penalty term is sum of absolute values of coefficients. Sum of absolute values of coefficients. Now, the difference also lies in the effects on coefficients. In ridge regression, the coefficients are reduced to nearly 0. They become very small, they take very small values, but they don't vanish altogether. They don't vanish, but their coefficients become close to 0 if they are not contributing significantly in the linear relationship. Now, but in lasso, you can shrink some coefficients to exactly to 0, effectively performing variable selection. This means that it can produce sparse model where some predictors are excluded. Now, this is the main difference which is intended to be asked, that in the use case, when to use which. So ridge regression is better when you want to retain all predictors and control their magnitude. And lasso is better when you want to perform feature selection and eliminate some predictors. But if you know the technicalities of type of regularization and effects on coefficients, then that is also good. But this is the intended way. What are the use cases? They will, if you, okay. So computational complexity, ridge generally speaking to compute, generally simpler to compute because the penalty term is differentiable everywhere. Lasso can be computationally intensive because the penalty term is non-differentiable at 0, requiring more sophisticated optimization techniques. So that was all for today. Thank you for joining me in this video.